At nearly 400 meters below the Atlantic, hydrostatic pressure reaches nearly 4 megapascals. That means every square meter of a tunnel wall experiences 400 metric tons of force pushing inward. If a hairline fracture opens in the rock face during excavation, water does not simply trickle in, it shoots through the fissure at velocities exceeding 60 meters per second, fully capable of stripping uncured shotcrete straight off the bedrock. Norway's E39 project is not just a massive highway upgrade. It is an aggressive, over $40 billion geotechnical experiment designed to replace 7 coastal ferry routes along an 1,100-kilometer corridor, headlined by the Rogfast connection, a 27-kilometer twin-tube tunnel reaching 392 meters below sea level. Chapter: The Hydrostatic Trap. To build at these depths, engineers are forced to contend with a harsh geotechnical reality. The deep, glacially carved fjords of Norway consist of highly jointed crystalline metamorphic gneiss interspersed with fault zones filled with weak, clay-rich gouge material. In a shallow tunnel, minor groundwater inflow is managed by internal drainage channels and sump pumps. At nearly 400 meters below sea level, allowing water to freely enter the tunnel envelope to relieve pressure is impossible. The sheer volume would require megawatts of continuous pumping capacity, and the unseated hydraulic gradient would cause progressive piping of fault gouge, collapsing the rock mass surrounding the excavation. The solution relies on high-pressure pre-grouting, but this introduces a dangerous engineering balance. Before blasting or boring each 6-meter round, long probe holes are drilled radially ahead of the tunnel face. Workers inject a ultrafine cement slurry into the rock matrix at pressures reaching up to 10 megapascals, or 100 atmospheres. This injection pressure must significantly exceed the surrounding 4 megapascal hydrostatic head to displace the seawater and penetrate microscopic rock joints. Here is the precise failure mode engineers fear most: if the grout injection pressure exceeds the local minimum principal stress of the rock mass, the process triggers hydraulic fracturing. Instead of sealing existing joints, the grout snaps the intact rock open, creating brand new, high-conductance fracture networks directly connected to the ocean above. If this occurs in a fault zone containing swelling clays like montmorillonite, the injected water and grout mix causes rapid chemical softening, reducing the internal friction angle of the shear zone to near zero and inducing structural tunnel collapse. Engineering crews must perform continuous, real-time Luggion testing ahead of the face, dynamically tuning the viscosity, setting time, and pressure profile of the grout to stay within an extremely narrow operating window bounded by hydrostatic head on the low end and rock fracture limits on the high end. Chapter: Drill and Blast versus Mechanical Excavation. Choosing the excavation methodology for a megatunnel at this depth comes down to a structural trade-off between speed, structural integrity, and in-situ stress response. While long, continuous civil tunnels typically favor tunnel boring machines due to high advance rates, large portions of the Rogfast project utilize drill and blast methodology, and the mechanics behind this choice reveal a key structural judgment. In deep alpine or subsea environments, the rock mass is subjected to extreme anisotropic stress fields. The vertical stress, driven by the overburden of rock and water, is compounded by high horizontal tectonic stresses stored in the Scandinavian Shield. When a TBM cuts a smooth circular profile, it creates a uniform stress concentration along the perimeter. In high-stress metamorphic gneiss, this concentration routinely exceeds the compressive strength of the rock, causing dynamic strain burst failures, where slabs of rock violently spall off the tunnel crown and walls without warning. Drill and blast allows engineers to alter the cross-sectional geometry on a blast-by-blast basis. By creating a horseshoe profile with optimized wall curvature, stress concentrations can be redirected away from vulnerable rock joints into stiffer, intact zones of the formation. Furthermore, drill and blast allows immediate access to the newly exposed rock face for the application of high-performance fiber-reinforced shotcrete and long, tensioned, fully grouted rock bolts. However, blast damage creates a microfractured disturbance zone, known as the excavation damaged zone, extending up to 2 meters into the surrounding rock wall. In a subsea environment, this damaged zone becomes a hypermeability ring surrounding the tunnel, effectively short-circuiting the pre-grouting canopy. Engineers address this by utilizing electronic digital detonators with millisecond delay timing, optimizing the shockwave interference patterns to fracture the interior rock volume while minimizing shockwave energy transmission into the surrounding rock perimeter. Chapter: Floating Bridges and Archimedes Tubes. While deep rock tunnels like Rogfast handle crossings where the seabed is accessible, central fjords like the Sognefjord present a completely different problem. The Sognefjord is over 1,300 meters deep and nearly 4 kilometers wide. Sinking a subterranean rock tunnel under a seabed at that depth would require approach gradients far too steep for heavy freight vehicles, and vertical stresses would exceed the compressive limit of almost any rock mass. To cross this gap, Norwegian civil engineers are developing submerged floating tube bridges, often referred to as Archimedes bridges. These structures consist of twin concrete or steel tubes suspended 20 to 30 meters below the water surface, held in equilibrium between buoyancy and anchor systems. The structural dynamics of a submerged floating tube are utterly unique. The structure is entirely disconnected from the seabed, meaning it acts as a continuous beam supported by an elastic foundation formed by seawater and tension mooring lines. The primary engineering challenge is not holding the structure up, but managing complex, coupled hydrodynamic forces. When deep ocean swells enter the fjord, they generate subsurface wave action that impacts the outer wall of the tube. Simultaneously, tidal currents generate vortex shedding, where alternating low-pressure eddies form behind the structure, inducing high-frequency vortex-induced vibrations. If these shedding frequencies match the flexural natural frequency of the multi-kilometer concrete tube, the resulting resonance can rapidly cause structural fatigue in the segment joints. To mitigate this, engineers are analyzing tethered tension link systems against floating pontoon supports. Pontoon supports provide high vertical stiffness but couple the tunnel directly to surface wave energy. Tension leg cables, anchored to the fjord bed over a kilometer down, keep the structure entirely submerged and isolated from surface motion. However, at extreme depths, the mass of the anchor cables themselves introduces axial elasticity, allowing low-frequency lateral swaying. To counteract this, structural models utilize active dynamic mass dampers inside the concrete hull, which shift heavy internal counterweights in opposition to wave forces, maintaining structural stability under 100-year storm conditions. Chapter: The Thermal and Safety Vector. Operating a closed highway system hundreds of meters below sea level creates unprecedented environmental and safety control challenges, specifically regarding thermal hydraulics and fire engineering. In a 27-kilometer tunnel with a 400-meter vertical drop, natural ventilation patterns are dictated by the stack effect, driven by temperature differential between the warm subsurface rock mass and cold fjord air, alongside density variations caused by vehicle emissions. In a fire event, these buoyancy forces act unpredictably. A severe freight vehicle fire inside a subsea tunnel releases thermal energy at rates exceeding 100 megawatts. This extreme heat creates a phenomenon known as backlayering, where a reverse layer of toxic, superheated smoke travels upstream against the forced ventilation air current, overwhelming emergency escape routes. In standard tunnels, longitudinal jet fans simply blow smoke toward the nearest portal. In a deep, sloping subsea tunnel, blowing smoke downhill against natural thermal buoyancy requires massive amounts of mechanical power. If ventilation velocities are too low, the smoke stratification breaks down, filling the entire cross-section of the tunnel with toxic gas. If the ventilation velocity is driven too high, it feeds fresh oxygen into the fire core, exponentially increasing the heat release rate and accelerating concrete spalling. To prevent explosive spalling, where moisture trapped inside concrete pores vaporizes and snaps off structural chunks, the tunnel linings incorporate polypropylene microfibers mixed directly into the concrete matrix. When exposed to high temperatures, these synthetic fibers melt, creating a network of microporous channels that allow high-pressure steam to escape without destroying the structural matrix of the lining. Furthermore, intermediate ventilation shafts are drilled vertically through hundreds of meters of solid rock to create localized pressure relief valves, isolating fire zones and preventing catastrophic smoke propagation through the entire underground corridor. Chapter: Systemic Integration. The upgrade of Norway's E39 highway is a fundamental masterclass in managing hyper-complex civil systems under severe natural constraints. By forcing structural engineering, rock mechanics, fluid dynamics, and thermodynamics to operate at their ultimate physical boundaries, Norwegian engineers are building a persistent land-based network across terrain that was previously considered impassable without marine surface transport. From high-pressure hydraulic fracturing management during pre-grouting, to hydroelastic vibration control in submerged floating tubes, every single element of the project trades off structural margin against extreme operational risks. The resulting infrastructure will reshape modern civil engineering standards for deep-sea subterranean transit, serving as the blueprint for future megaprojects across the globe. Given the extreme capital costs, potential failure modes, and continuous maintenance requirements of subsea infrastructure, at what point do you believe structural engineering constraints should dictate that we accept the natural boundaries of geography, rather than forcing land-based transit through megaprojects of this scale?